Now, let's take a look at how these work if I've got capacitors, more than one capacitor in a circuit. Let's say that I've got we'll look at two capacitors, and we'll look at two capacitors, and then we'll be able to, from this, generalize out into any number in either series or parallel. There's some change in potential between point A and point B, and likewise for these two in parallel. Heck, let me write AB is not 0. Okay. In series, from this equation, what do I know? Well, I know that the change in potential from point A to point B is equal to the change in potential over capacitor 1 plus the change in potential over capacitor 2. So, if I say, okay, well, let's hope, well, also that the change in potential is equal to the charge stored on the capacitor divided by the capacitance of the capacitor. Now, the other thing that we know is that, okay, imagine that I've got some electric potential over those cases. Say I have like an electron come in from one side, stick to one side. That will induce a positive hole on the other side, freeing up an electron, which will go as far away as it can, hey, to the opposite plate, freeing up a positive charge, a positive hole on the other side, freeing up, hey, an electron. And as electrons move through, building up on these plates, then the amount of charge on each set of capacitors has to be the same. The charge on capacitor 1 has to be equal to the charge on capacitor 2. Now, if I look at this and write this as, okay, what's the change in potential over thing 1? That's Q1 over C1. What's the change in electric potential over thing 2? Q2 over C2. Now, these two charges have to be the same. So let me just say that equals some charge Q, and I want to write, if I have, oh, here's the change in potential over a set of capacitors, what we want to hope for is we can look at this in terms of one representative capacitor. So I'll say the total charge divided by the equivalent capacitance of that set. Now, the charge is the same in each case because the total charge on the capacitors, if I were to look at this positive plate and that negative plate, that has charge Q. which is the same as the charge Q1, which is the same as the charge Q2. So 1 over the equivalent capacitance is equal to 1 over C1 plus 1 over C2, however many capacitors you have in series. So 1 over the equivalent capacitance for any number of capacitors in series is 1 over C1 plus 1 over C2 plus however many other capacitors are in series at the same time. Now, if I have two capacitors in parallel, remember that if I'm not running out on you, two objects that go from the same point A to the same point B, then the path they take from one to the other does not matter. They've both gone through the same change in potential. So what I've got here is the change in potential over capacitor 1 has to be equal to the change in potential over capacitor 2 has to be equal to the change in potential between point A and point B. Now, each one of these represents a different path. Each one can build up a different charge. So the charge on the equivalent capacitance of that whole deal is equal to the charge stored up on capacitor 1 plus the charge stored up on capacitor 2. Q is equal to C times the change in potential. So the capacitance of the equivalent imaginary capacitor, where one capacitor represents however many we have in parallel, times the change in potential from point A to point B, is equal to C1, times the change in potential over capacitor 1 plus C2 times the change in potential over capacitor 2, but all three of those are the same thing. So I can write that for any number of capacitors in parallel, the equivalent capacitance is equal to the sum of the capacitances of all the capacitors involved. Now, I'm going a bit faster than I would go through lecture, because if there's ever a point where it's like, I do not have that written down, you can pause, write it down, and then come back to where we are. So, for parallel, the equivalent capacitance is equal to the sum. Now, let me see how much time I've got. Okay. There are two things I want to call to your attention here. First, notice that if I've got capacitors in series, the total capacitance is always going to be less than the least capacitance involved. Why? Because, again, let's anthropomorphize the heck out of this to make it clear we're dealing with a model here. An electron, as electrons go through this path, then they've got to deal with both of those capacitors. In this case, an electron can be stored on either capacitor. So if C1, that looks full, it can go and get stored on C2. So here, the capacitance is the highest it would ever be. Now, let's suppose, as a quick example, that I've got C1, a 3 microfarad capacitor, a 12 microfarad capacitor C2, and a 6 microfarad capacitor C3. To find the total capacitance of that, 1 over the equivalent capacitance is equal to 1 over 3 microfarads plus 1 over 12 microfarads. I'm going to need, I think, to deflect this just a smidge. Plus 1 over 6 microfarads. I'm going to stop here and start the next one as an example